Get started. So good morning, everybody, and welcome to our webinar series hosted by Enercon Engineering's Integrated Defense Solutions Business Unit, or IDS for short. I see we have some returning viewers, so that's great. Thank you guys for your continued support for watching these webinars. And we also have some new viewers, so welcome and glad to have you on board. If you don't know, Enercon is your power integration solutions expert. We have our main facility, which is located in East Peoria, Illinois. That's where Mac is located. On your screen, he's there at the main facility. That's where we do all the designs, manufacturing, and testings for all the products that we produce. We produced over 40,000 projects, not only here domestically in the U.S., but also abroad in about 110 different countries. I'm your host, Sean Lott. I am the Director of Business Development. I am located in the Enercon Business Development Office in Huntsville, Alabama. This is our 5th webinar in our 2020 series. If you missed any of the previous webinars, visit our YouTube page. I put a link in the chat box where you can copy and paste it into your browser, or just click the link and it'll take you right to our YouTube page. And there you can see all of our webinars from the past webinars that we did this year, as well as other informative videos that Enercon has produced, highlighting our 45 years of history. We just turned 45 years old on September 2nd, so we were happy to have a ribbon cutting earlier this month at our main facility, as well as a celebratory social distance type of celebration on the 2nd, so that was great. Before we get started, I just want to give out some ground rules as far as questions go. Don't be bashful with your questions. All you got to do is click the Q&A tab in the Zoom bar and then type in your question. Nobody will see your question but me. I'll get your question and I'll put it in the queue for Mac to answer those as we conclude today's presentation. Our aim is to address all your questions at the end of the presentation. So feel free to ask away. As a reminder, this session is also being recorded. It's being recorded for on-demand viewing, which that can be done on Facebook or on YouTube at a later date. Now I'd like to introduce today's presenter, McClean, or Mac Wendt, or Mac for short, Wendt. Mac serves as Enercon's IDS primary electrical engineer and test director. He has over 10 years of testing experience. Additionally, he has experience on numerous commercial projects as a design engineer, applications engineer, and a project manager. So without further ado, Mac, over to you.
So today's presentation is going to be primarily an overview of testing power systems. And if there is further interest, we can set up later webinars to explore more in detail some more in-depth topics such as paralleling techniques, data analysis, and such. But please give us your comments and feedback so we can address those in time. We'll be talking about power systems, the hazards of testing those, equipment, and the various tests that we do typically in power systems testing, and also what we do when we find issues, since that is primary reason why we test the systems, is to flush those issues out. So the power systems, typically what we're looking at is a generator engine set, and primarily, we test units that are between 0.5 megawatt to 3 megawatts, or systems that are in that range. And typically those are fueled by either diesel or natural gas. Although that's what we typically do, now with increased demand for microgrids and renewable sources, We're seeing an increase in addition of energy storage systems. It could be supercapacitors or batteries, and solar power integrated into these systems. In addition to those power systems, we've also seen specialty applications where engines have driven pumps, and all those we can test and verify proper operation before passing them on to the customer. So first and foremost, we put safety ahead of everything else. We want to make sure that everyone goes home safely and no one's injured. And in testing these unproven systems, there are a lot of dangers and hazards. There's electrical hazards or shock, in the worst case, electrocution, arc flash, which can cause explosions. And then we also have lots of mechanical dangers with rotating mass that can either throw parts or personnel can get caught up in the equipment. There's high temperatures, high pressures, fumes, and also they're very noisy when we're testing. So all of these need to be addressed, and we need to take measures to mitigate risk to both personnel mainly, and then secondarily to reduce the risk to the equipment, both the testing equipment and probably more importantly, the customer's product. So for precautions, first we start off with personal protective equipment, which is glasses, safety toes, hard hats. Those are typical PPE that we do throughout our production and test. There are some additional PPE that we use for testing, like HR clothing, heat-resistant clothing, and hearing protection, because we are constantly around the noisy engines. So when we're setting up a test, we need to be mindful of all of these hazards, and we need to be mindful of egress and proper spacing both for cooling and also to make sure that if a technician needs to get into a tight location, that they're able to get out safely in case there's an incident. And then we also take care in marking all the hazards and setting up barriers to make sure that people don't accidentally or intentionally, for that matter, go into a danger zone. And those are very important, especially when you have visitors, either customer or even non-test personnel in the test area. We need to make sure that those are the dangers are clearly identified, and those visitors know proper places to be and not to be. So our procedures are also, first we look at safety. So when we're building a procedure for a test, first we want to test out all the safeties as soon as we can. So like emergency stop push buttons. We want to make sure that those are in working order before we start the engine or provide energy to the system, because if there is an incident, we want to make sure that we hit that emergency stop button and the system transitions into a safe state, along with any other safety switches or sensors that are going to protect personnel and equipment. Then the most important thing in safety is the team, both to protect the team and then also having a trained and vigilant team that looks out for each other and themselves to make sure that the priority is that no one gets hurt. And so we've definitely demonstrated this over 6 years. We've had no lost time due to accidents, and that's for the facility as a whole. Beyond that 6-year period, I still can't remember when we've had a significant incident in test, or at least not one that I've been involved in. So so the equipment is important and when setting up the test, we have to simulate whatever the power system is supplying. And so that's going to be a distribution system of some sort. Those will compose of circuit breakers, resistive, reactive load banks, and load transformers. So circuit breakers are important to provide protection in case there is a fault. Also for isolation, so that the unit under test can be isolated for certain tests. If we are hooked to a load transformer, if we're doing a lot of starts and stops, we may not want to be energizing and de-energizing a transformer. The resistive and reactive load banks are used to simulate the loads that the power system is going to be designed to support. The reactive component of that creates the power factor, and those can be either inductive or capacitive. We typically use inductive, but have had times where we've run tests with capacitive, and we just need to rent the correct load bank if we do not have the right one on our lot. The load transformers will step down the voltage. Typically used for medium voltage, we'll step it down to 480, which is a typical supply for our load banks. But we have also had projects where we deal with various different unusual magnitudes that we need to get back down into the right range for our load banks. Both with the load banks and the transformers, one key thing is the frequency. So if it is not a 60 hertz system, then we need to make sure that our transformers and load banks are matched to whatever that frequency is. If it's 50 or 400 hertz, or even DC. We've got a project coming up that we've got a 800 volt DC system that we're testing. So you need to be mindful of that, and you're keeping your test within the ratings of your equipment. Sensing, we've got metering transformers and transducers. Those are sometimes external. We put our own external ones on the units to test them, or sometimes we can interface with the generator's own metering transformers. And those will report to a data capture device. We have data recorders, power quality analyzers that we use to record for record and also to evaluate the performance of the units. We also, depending on what controller is on the generator, we can also access the logs and do that for additional record of the test. The mechanical portion to support the engine includes fuel system, fuel supply, exhaust system to get rid of those dangerous fumes that we're talking about, and also dissipate some of that noise. A lot of that dissipating that noise is the mufflers, a lot more for our neighbors to make sure that we're being good stewards. And then remote radiators. Sometimes the engines have remote radiators. We've got a remote radiator farm that we use for testing engines that don't have their own cooling system. Okay. So there's several different tests that we typically perform on power systems, and these are going to be governed by the design and the requirements of the customer. So with functional testing, again, we want to do any of our safety testing, any of those devices that are going to protect the equipment and personnel. We want to make sure that those are tested first and function accordingly. And then we'll want to go through all of the controls to make sure that all the non-operating controls are displaying correctly, reporting the status of the auxiliary systems correctly, all the communications, all the devices are communicating properly. And then we're able to move into startup. So when we say startup, that's going to be when we start up the engine generator for the first time, or start up the system for the first time. And we'll start it. Sometimes we'll start in idle and make sure that everything's spinning the correct way. And if we can, test to make sure that things are being, everything is being sensed correctly. And then we'll move into rated. So the engine will start spinning at 1800 RPMs, typically for a 60 hertz unit. At that point, then we'll make sure that all that the voltage is coming up to the right level, that the phasing is correct on both the sensing PTs and the load. We'll make sure that the CTs are also have the correct polarity and are reporting to the controller the proper values. The next step would be to test alarms and shutdowns. And so we'll simulate various different alarms that we can do safely. Some we may do by changing a set point to verify that alarm is capable, or a controller is capable of that alarm. And then other situations we'll simulate by actually creating that condition. So for a low coolant level, we may end up draining off some of the coolant from the expansion tanks of the radiator until that alarm trips, and we'll get a warning. And then if there's a shutdown, we'll drain it down to that shutdown, make sure that the engine transitions to a safe state. So after we're sure that all of our protections are working correctly, then we can go into paralleling. If the system is set to parallel with other power sources, or if the system itself has multiple power sources, multiple generators in there, we'll do paralleling, make sure that each source can synchronize to each other or to an external source, and that they're sharing load properly. And then finally, auxiliary systems, make sure the jacket water heaters work, battery charging system, all of the things that are there to support the primary purpose of the power system are all in working order. So moving from just the pure functional testing, then we want to also look at the performance of the power system. And for those, we'll be looking at the metering on both the current and voltage, all three phases. And we'll have a power quality analyzer that we can check waveform, harmonics, any of those things that are fundamental to the generator of the power system itself. When you're doing that testing, typically you want to run that on just purely resistive load bank, so you're not having an effect from your reactive load bank. And you're just characterizing the generator under test. It's good to do that as soon as you can, in case you do have an issue with the way that the generator is wound. You're not going to end up wasting a lot of fuel and a lot of testing if you end up having to pull that generator and send it back to the manufacturer to be rewound. So the next part, it would be transient performance. This is adding and dropping loads quickly. That's the graph in front of us is characteristic of a transients. And those will just, whatever the load profile that we go through is going to be governed by the customer and what their power needs are, including their requirements of what the overshot is for frequency and undershot for voltage. Or, all of those will be determined by the customer. And then there's voltage stability and frequency stability to make sure that if you're running over a period of time that your voltage and frequency are not drifting away from the nominal rated value. And then finally, endurance tests can be run just to shake out any of the bugs or early problems that you might have on a system to give better reliability. And we've done all sorts of durations, whether it's 4 hours, 24 hours. We have a large project that we typically run for a week straight, 24 hours, 7. And then there was a picture earlier of tests that we did for 30 days straight on 2 units with 4 generators between the 2 of them. So those will help prove the resilience of a system. Yeah. So why do we test? We test to shake down any of those issues. Anything that is either a flaw of manufacturing or a flaw of the design itself, we want to make sure that the product itself performs the way that the customer wants and needs. So when we come into an issue, the first thing that you're going to do is start troubleshooting the issue, what the issue is, what's causing it, what are the possible causes of it. And if you can find that out quickly, that's good, because then we can, the best thing to do to make sure that you have full honesty and trust from your customer is to also be very open. So if the customer is not there, to make sure to notify them. I like to spend a little bit troubleshooting to make sure that I have a good understanding of what the situation is before I talk to the customer, just to make sure that we don't get people worried about something that's a minor issue, and to try to just try to control it. But if it's taking too long, then we need to notify them right away. Once you've troubleshot the issue and found out what the issue is, you do the corrective action. Oftentimes, depending on what it is, if it's small, then we can fix it or send it back to production to have them fix it. And then the next part would be once the corrective action is approved and implemented, I need to figure out what kind of regression testing needs to be done. Does any of the repair disqualify or invalidate the results from previous testing? Or can you just continue on from where you were at? And that, again, is just done in the open with the customer to make sure that when we do the final reporting and we tell them what the issue was and how we resolved it, and how we continued on with testing to verify that there wasn't anything else, they can trust that was fully vetted, and not have a question that we need to go back and redo some testing, burn unneeded fuel and time. And what I found is just having that open and honest relationship with the customer really helps out in the early troubleshooting, because have several customer engineers I've had good relationships with, and they know that I will always tell them what the issue is directly, and they will give me space to do the troubleshooting without peppering me with questions at that time.
Well, thank you so much for your expertise and your insights on how we test our power systems. That was some great information. And just so you know, I'm still waiting on some questions, so it's still not too late to submit a question if you have one. As a reminder, just click the Q&A tab and send in your question. It's anonymous, so nobody will see it but me. I'll read your question, and then I'll pass it on to Max to see if we can get him a good answer for your question. So with that, I do have 3 that have come in thus far. And one of the viewers wants to know, how is testing data recorded and analyzed?
Okay, so I mentioned normally we use sensing PTs. Well, I guess let's start off with just the voltage and current. So normally we have PTs on potential transformers and current transformers on the equipment, either on the system itself that we can tap into if needed, or external PTs and CTs that we can hook into our own data capture system. So we use Fluke 1750 for data logging. It also does some power quality and harmonics recording. We also have a Dranitz meter, which also does logging and power quality. So those are the primary ones that we use. We've used Fluke NetDecs in the past with transducers for long-term strip recording, but some of the newer meters that we have more capability.
Okay. All right, and our next question deals with test reporting. So they want to know, what do you typically include in a test report that Enercon produces?
Okay, that depends on the project, depends on the customer. So for a military project, we have a well-defined um, acceptance test plan with developed acceptance test procedures. And so we follow that. That has been developed over the past decade. I wrote most of those procedures with our customer engineers and input. And throughout the years, we've revised those, made them better so that we can detect issues sooner, less costly to the program. So those procedures themselves become the report, with just adding in the charts for the charts that show the performance with the criteria of the customer or this program marked clearly, showing how the performance is better than the requirement. And then after that, then it's all reviewed and signed off from both us and our customer and our customer's customer. And then for commercial projects, it's usually less vigorous. So we'll provide our procedure with marked off each of the procedures that we've performed, and then we'll supply either in the report or as a supplement the complete data set. And if they have communicated to us particular requirements that they want to meet, then we can also provide a chart that shows their requirement and how the unit performed relative to that.
Okay, interesting. And our last question, and before I get to that, if you have a question, feel free to hit the Q&A tab and ask it, as this is our last question we have from Mac, and we don't want to let him off the hook that easy. So here you go, Mac. What is the most time-consuming part of testing these equipment, or these systems, I should say?
Definitely troubleshooting. I mean, set the tests up, and always, especially when you're doing tests as the same product over and over, you do the corrective action, make sure that you check the things that have been time consuming before, but then you always have new issues that arise. And those ones are those unknown issues that you're going to come across are the ones that just eat up time. And then we normally just have to push through, figure out what the problem is, and get it resolved, so we don't, if we can, so we don't push schedule. But sometimes that's unavoidable depending on what the issue is. But that troubleshooting process, because for the most part, everything stops. Oftentimes it's me and my technician, we're working through it, and it's very hard to multitask when you're trying to troubleshoot an issue. You want to really just focus in and eliminate all the possible issues, and sometimes have to branch out and request help from other experts here at Enercon or with the customer or the supplier, depending on who they are. So it really bogs things down, and need to be mindful of that when we do set up the schedule. You can't set up a 4-hour test for 4 hours when you know you're going to have some issues when you're starting things up.
Yeah, exactly. And I'm sitting here thinking, like, one of the most precious resources that we all don't have enough of is time. And so what's good about what you're doing is and it kind of goes back to the truth and honesty, is you are upfront with the customer, and you let them know exactly how much time is required in order to adequately test out these power systems. And sometimes it could be a surprise to some folks on how long it actually takes to do a fully vetted test on a system. Because what we don't want, and it goes back again to trust and honesty, is to produce a product and we ship it to a tactical setting, in this case, let's say in support of the warfighter, because we do have products that support Department of Defense all over the globe. And that product doesn't function as it's designed to do in an austere environment based on the conditions that it's in. So it behooves us to ensure that we go through the testing just like how you laid out, to ensure that we have safe, reliable, dependable systems that support not only warfighters from a defense perspective, but also for our commercial projects as well, which is it's proven that we do that around the globe. So I just wanted to just highlight that point. So thank you for that. So let me check the Q&A. I don't see any more questions in the question tab. So thanks again, Mac. Very, very informative session, and we're glad that you were able to do this for us, and we really do appreciate it. For you, those of you guys that are witnessing this right now, you'll receive a on-demand link, so you can go back and look at it. You can review it if you missed something, or you had to step away, or whatever the case may be. Or better yet, you can share it with your colleagues. So share the link with your colleagues. It's always doesn't cost much of anything to learn, especially from us. We're kind of open komodo, so these are free sessions that we just offer for your benefit. And don't forget, it's also going to be hung on Facebook and YouTube as early as this afternoon. Our last and final webinar for this year, for 2020, will come from our sister business unit, the Integrated Energy Solutions Business Unit, and that's going to be held on the 27th of October at 10 o'clock. We're still finalizing what the topic is going to be, but it's going to be great, whatever it is. And we're going to send you a personal invite for those of you that have been in attendance with us today, as well as past attendees. And if you would like to add some folks to our distro list to be part of this, just shoot me a note or reply back to the survey as well with that information, and then I'll ensure to include them on our distro list. So with that, I want to thank you all for joining us and taking time out of your busy day to learn and grow with us. And you guys have a great week. Thanks, Mac, and I'll see you soon.
Thank you, Sean. It's been a pleasure.